Forgot to record. So, X is normally distributed. That's the information we have. X has a mean of 30. That is the mean. So, to determine the proportion of video package that will get bad, we want to find the probability that the lifetime will be less than, let's say, A. That A is the guarantee period. The time it will take for it to be refunded. That's the guarantee period. You will only refund video that will get bad within the guarantee period. Is that right? So the probability that a video, a lifetime X is less than A should be what? Should be what? That is the proportion of video that will be refunded, isn't it? The proportion of video that will be refunded is the proportion that will get back before the guarantee period. So what is the proportion of video that will get back before the guarantee period? According to to what they want. Yes, 7%. Do we get that? They do not want to refund more than 7%, meaning that they do not want more than 7% to get bad. So the quantity that should get bad should be what? Less than 7%. Is that right? If you don't want to refund more than 7%, that means you want that the quantity that will get bad should be less than 7%. Do we get this one? So we will say less than 7. If you write 0.07, that will mean that if we put A here, this area is what? What will be this area from what we learned last time? It will be 0.07. The area to the left of a number is the probability that the random variable is less than that number. Do we get this? Okay, so we are going to put here 0.7. So let's say that we don't want to do the mathematics involved because we know how to use calculator. The question now will be, what is the value A so that the area to the left of A is 7%? Can you find that using your calculator? Find this number so that the probability that X is less than A is 7%. Anybody knows how to do that? Somebody does not know how to do that? You know how to do it? Inverse normal. Do we remember that? It's by practicing that you will know. This calculator might look confusing to you now. Just like when you just bought a new phone. You will not know where to even answer calls. Sometimes you don't know. 2-3 days later, you know everything because you are using it. Do we get that? If you don't use your calculator, you will not like it. If you use it, you will love it because it's going to save us a lot of problems. I will show you what to do if you don't have a calculator while you are using your calculator. So we want to find the probability that X is less than A is equal to 0.07. Normally what you will do is to find Z so that the probability that Z is less than ZA is equal to 0.07. To do that, you will go to the table. I showed you the normal table last time. And you will look for 0.07 and identify this Z value there. Once you get that Z value, you will come back and solve it here that you start from here. Z is X minus mu over sigma. So that means sigma z x minus mu, and x equal to sigma z plus mu. You use this formula when you know your z. So this is how you will get to your z. I am taking this time because I know I want you to at least see how you are supposed to do it manually using your the table. So I'm looking for standard normal distribution table. This is the standard normal distribution table, and I want to find my z. Then I go and inside here, I'm looking 0.07. You can see 0.07. We are here at 0.07. I will be going down to reduce it. This is 0.0694, 0.0778. So it's between these two numbers. 0.0707, 0.069. Which one is closer? Is it 0.069? So now the z value is negative 1.4. The z value is ZA is negative 1.4, and I will look for the second decimal. That second decimal is 8, 7 or 8. Then I am going to come back here to replace and have negative 1.48 times z, that is z, times 4 plus 30. What do we get? Can somebody use the calculator to get this? You already have your calculator. Before we proceed, can somebody tell me what is x? You go to second portion, distribution, inverse normal, area is 0.07, mean is 30. If you have parentheses, you will have inverse normal, area 0.07, mean 30, standard deviation 4. What do you get? $24.21. So please check that you can use your calculator. You see the computation I'm doing here, I want to save you from doing that. So can somebody do this one? 30 minus 1.48 times 4, or minus 1.48 times 4, then add 30. So find ZA so that the probability that Z is less than ZA is equal to 0.07. You will find ZA. You don't really need this. I do sometimes this for completion. Do you know what I mean, completion? If somebody is checking my note, you will know that I taught you that. But I want you to know how to do it, because this one you will forget. Using that calculator, you will not easily forget. Okay? So you want to know that you can do it manually this way, but that should motivate you to get used to your calculator. So you will do here negative, you see, to even write is not easy. Negative 1.48. That is Z. So X is equal to sigma Z plus mu, which is 4 times negative 1.48 plus 30. Can somebody tell me what it is? 24.08. So this is the way you would have done manually without a calculator. So that will mean that if you do not want to refund more than 7% of the video, you should place a guarantee period at 24 months. If I ask you this type of question, don't tell me 24.1 months. If a company is doing that, people are not going to come to buy because a lot of people will be struggling to understand what is 24.1 months. Do you get what I mean? What I mean here, you just put it 24. So 24 months is the guarantee period. So if you go on the PowerPoint on Canvas, you will see the same solution. First, you use the inverse normal formula, or you can use the normal distribution table as you see here. Identify where Z is and solve the problem. So, normal distribution is very nice to work with. You know how when we were computing probability, it was not always very easy. And then we learned how to use the binomial distribution. There are more type of distribution like the geometric. Just roll a die until you get number 6, for example, or you get a number less than 3. Things like that, that different type of distribution. The advantage of the normal distribution is that it's a general distribution. That's why we give it normal, the name normal, because a lot of things behave like that. And most of the time in research, our question will just be, is the distribution of what we have normal? A normal distribution, as I told you, has some of the properties that we have. But when you are going to determine if the population you are dealing with is normal? One of the easiest methods is to take a sample and construct a histogram from it. The histogram might give you a feeling whether that distribution is skewed, normal, or any other one. So that is the first thing to do. The second thing to do is if you have your sample, you can compute this Pearson index value, which is the difference between the mean and the median times 3 over standard deviation. If this number is greater than 1 or less than -1, it indicates that it is skewed either to the left or right. Number which is greater than 1 or less than -1. Actually, what we are saying is that if the number is between -1 and 1, it is approximately symmetric. X is between -1 and approximately symmetric. Outside, it is not. There is also another technique which is called the normal quantile plot. You can use Excel or your calculator to do that. We are not going to be doing all of those in this class because we are always going to assume that our distribution is normal or give conditions for it to become normal. This class does not have that luxury of studying how to do all of these things. But I'm informing you, in the future, your calculator and Excel, you will enter your data and just get those numbers. And once you get those numbers, you can determine if your distribution is skewed or not. So if the distribution is symmetric, we don't mean that it is normal, but generally people accept that it is normal. This condition only helps us, actually, it is useful to tell that the distribution is not normal, more than to tell that it is normal. But when we know that we cannot say that it is not normal, people generally accept that it's normal. Are you getting this logic? So we don't really have that method of determining strictly that the distribution is normal. But we have methods to show that we cannot say it is not normal. Sampling distribution. Chapter 6 is moving us back to statistics. Okay, so if you did not enjoy probability, start feeling better. We are going back to statistics. As I told you at the beginning, statistics consists of collecting organizing, summarizing data, then analyzing it in order to make inference about the population, which are generalizations, or making predictions. So, descriptive statistics, chapter 1, 2, and 3. Probability is 4, 5, so that as we are speaking the language of probability in our statistic, you should not be completely blank about it. It's a measure of uncertainty. So we say that in order to study a population, we get a sample. As we get that sample, we want to make inference about the population. In order for that inference to be acceptable, the sample should be a good representation of the population. Do we remember that? And a good representation of a population, what did we call it? A random sample. A random sample. So think about it this way. I have a large population and I want to take a random sample from it. What I will be doing is the probability experiment. Just like I say, you have 50 balls and you randomly select 10. That is what we are actually doing when we have a population of 300 million people and you randomly select 20,000. What you are doing is a random experiment. Do we get this? You are doing a random experiment. Each random sample is an outcome of a random experiment. Each random sample is an outcome of a random experiment. Now, we defined a random variable as an association between outcome of a random experiment and numbers. So some of the examples were you toss a coin 3 times and you count the number of heads. So to each outcome of your experiment, you associate a number. Now suppose I say we have a population of 50 individuals. You take a random sample of 5 of them. That will be your outcome. Associate to it, for example, their average score on the test. That will become a random variable because to each outcome, you are associating the mean, the sample mean. Do we get this? Do we need to write all of this? We don't need to, I will not ask you to tell me, but I want you to just have a feeling of understanding of what it is. Because if you want to write all this, it will be a lot of writing. We will not finish this course. But I want you to get the idea of random experiment producing outcome that generate numbers, which we call random variable. Now, when we do a statistics, we collect samples and we want to think about those samples as outcomes of a random variable. I'm sorry, outcome of a random experiment. What we want to discuss in section 6.4, which we may not even write anything, if you understand what I'm saying now, is that each time we associate to a random sample a statistic. Remember, statistic is a measure of a sample. To our random sample, if we associate a statistic, that can be the mode, the median, the mean, the standard deviation, we are defining a distribution which is called a sampling distribution. Even when you speak about it so much, it is not always. So we want to start by recalling here that a statistic is a measure of sample. A parameter is a measure of the population. So measures of sample, these are the notations so that we remember. The last one, which is proportion, we have not really talked much about it, but it's not something complicated. A proportion, sample proportion, is P hat is equal to X over N, where X is the number of success and N is the sample size. For example, if you take a sample of 30 individuals, you might want to say, what is the proportion of female? If there are 10 females, then the proportion is 10/30. Do we get what that means? Proportion. We know what proportion is, right? That's why I keep teaching proportion here. So this is the formula for proportion. We can best understand it by thinking about it as a binomial experiment, in which X is the number of success and N is the number of trial. So proportion, if I toss a coin 10 times, what is the proportion of head? Number of heads divided by number of trial. That is proportion. If I roll a die 20 times, what is the number of time I have a number less than 3? That is proportion. So I want to use that to explain more about statistics and parameters. If I toss a coin 20 times, I might have P hat equals to maybe 9/20. It's possible I have 9 heads instead of 10, right? But what we call parameter is the probability of success for tossing a coin is 1/2. This is the theoretical value, and this is the empirical value you obtain from your own experiment. So generally, we are suspecting that if we know this number, it can tell us something about this one. And that is the main purpose of statistics. How to use what you get from the sample to have an inference about the population. So now, the sampling distribution is a distribution of statistic. For example, sample mean is a statistic. We will call it sampling distribution of sample mean. If we take proportion, it's a statistic. We will call it sampling distribution of sample proportion. If we call it the standard deviation, we will call it sampling distribution of sample proportion. This distribution is from the fact that we know getting a random sample is a probability experiment. Because our random sample is a sample, we can compute either its mean, a proportion, or a standard deviation from it, and it will define to us a random variable. So from now, we are going to be looking at the sample mean, for example, as a random variable. So the sample mean is a random variable. Our question is, what is the mean of that random variable? What is the standard deviation of that random variable? Let's compute the mean of the random variable of yes. This is all the sections. Is that what everybody is seeing? The PowerPoint is so mixed up that you can't read. The typing got mixed up. Anybody see something like that? I cannot. I just downloaded mine now. I think this one is better. So use the download. When you are on the PowerPoint, yeah. So you click here. Let me see how mine is. I've never looked at it. I always just download. There are a lot of things that happen with computer that we cannot explain. So, but if you use the download, I believe it will work. So now, let's get back to the normal distribution. The distribution of sample mean. What can I write here? So sample mean is, remember sample mean? X bar equals to sum of the X divided by N. Where X is population. We are doing a demonstration here, mathematical computation here. If you don't like mathematics, don't worry to write it. I will not ask you to do that on an exam. Sometimes I want you to see something. When you see and feel like it is right, you will remember what it is much later. So this is a random sample. We say every member of the population can be part of it. So for example, if X was the age of individuals, then when you take any individual at random, is a random variable also. Do we get that? Like if I say, I want to pick a student at random and associate to that student his age. That is a random variable. Now, if I can pick any member of the population, then the mean of that age is the population mean. The mean of X is the population mean. So that's why sometimes we call X here any value that a random sample can pick. We call it the population random variable. So what we are saying now is that if you have 30 of them, you pick them randomly. So each time you are picking them, it could be anybody. So it could be any member of the population. So X runs through the population. So the mean of X is mu. And the standard deviation of X is sigma, the population mean. Where mu is the population mean, sigma, the population standard deviation. So if we have that, our question will be, what is E of X bar? E of X bar will be E of sum of the X divided by N. Remember when we did with linear transformation, if you multiply a random variable by a number, you can take that number out of the mean. For that reason, I can take 1 over N out. And it will be E of sum of the X. Now, sum of the X is like X1 plus X2 plus X3 plus X4 up to N. We say if we have 2 random variables and you add them up, you get another random variable. Remember that our W when we were doing X plus Y, X1 plus X2. That helps us to say that when you do this expectation of the sum, it becomes the sum of the expectation. Expectation of the sum is the sum of the expectation. That's what I did when I say E of X plus Y equals E of X plus E of Y. Expectation of X plus Y is expectation of X is expectation of Y. Because of that, I can change this to 1 over N. The E will get into the X. There are N values that we collected from the sample randomly. Each of those values is a random variable that represents the population. So their mean for each of them is mu. And you are going to add them N times. So this becomes 1 over N. Each E of X is mu. You are going to add mu to itself N times. It becomes N times mu. We are going to have N times mu, and this becomes mu. What we are saying here, if you don't like this mathematics, I understand, but remember that the distribution of sampling mean, the sampling distribution of sample mean, has mean the population mean. The distribution of sample, it is on your PowerPoint. The distribution of sample mean as mean the population mean. And what will be the variance? The variance of X X bar is the variance of 1 over n times sum of the x. I just separated the 1 over n instead of just putting it under. So that we see it's like a. Variance of ax is a squared and variance of x. Remember that. So we are going to write this as 1 over n squared times variance of sum of the x. Having that, we want to handle variance of sum of the x. Remember we say variance of x plus y was variance of x plus variance of y. That's what I'm going to do here because the coefficient a, b are 1. So this will become, that's why we were doing those things. This will become 1 over n squared times sum of the variance of x. And this is equal to, using the same idea we have, n times sigma squared. And the variance of x is sigma squared over n. Sigma squared over n. So the standard deviation, look at what I'm writing here, very important. This is the standard deviation of the sample mean. The standard deviation of the sample mean will be the square root of the variance of the sample mean. Square root of sigma is sigma, and here we will have square root. So what we have said so far is that the sampling distribution of sample mean has mean mu, the population mean, and it has standard deviation sigma divided by square root of n. Okay? That is what you should remember from this section. The standard, the mean of the sampling distribution of sample mean is mu, but the standard deviation is sigma over square root of n. I'm going to consider the other one, which I'm not going to write. It's so difficult writing this. So this one is already good. So for you in class, because those on Zoom cannot see this. So we say that the sample, this sample proportion is x over n. When x is the number of success and n is the number of trials, we know that E of x is equal to what? Anybody remember? NP. E of x is equal to NP. And sigma x is equal to what? For a binomial distribution, square root of NPQ. We are going to do the same thing I did for the sample mean for sample proportion. So we are going to say that the mean of the sample proportion is E of P hat, which is E of, this one is easier, x over n, which is 1 over n, E of x, which is 1 over n, NP, which is equal to P. And this means that the sampling distribution of the sample proportion is the population proportion. What are we saying? That the expectation of a sample proportion is the population proportion, which is what we want, right? When you are dealing with a sample proportion, you expect to get a population proportion. When you are dealing with the sample mean, you expect to get the population mean. That is what we are translating statistically. And the variance, let me write it like this. The variance of the population proportion will be variance of x over n, which is 1 over n squared, variance of x, which is NPQ divided by n squared, which is PQ divided by n. So the standard deviation of the sample proportion is square root of PQ over n. So we have considered two statistics, and we have defined the sampling distribution of those two statistics, and we have computed their mean and their standard deviation. What we don't know is the nature of those distributions. What is the nature? That is, are those distributions normal? Okay, are those distributions normal is our question. This is not what I want. So we have an important question here. Next question is, what is the nature of the distributions? That is what chapter 5 is going to answer. What is the nature of the distribution of sample mean? So this theorem tells us that if a distribution is normal, it's good for things to be normal, right? People say that's not normal. If it is normal, it's good. You want to remember that in statistics. So if a distribution is normal, that is, a population is normally distributed, then the distribution of sample mean will also be normal, and there will be no problem. The distribution of sample mean is normal if the population is normal. But if the population is not normal, we may want to have a large enough sample for the distribution of sample mean to become normal. That is what the central limit theorem is going to tell us. If the distribution is not normal, we may use the central limit theorem, which says that if the sample size is large enough, then the sampling distribution of sample mean is approximately normal. So we want to say that, it seems as if I have not mentioned, you see here, if the sample size is large enough, if the sample size is large enough, I will add here at least 30. So this is just what we will be using in this class. But in general, it will depend on the level of skewness of your sample. You know, when we look at a histogram, you see some are really skewed, some are skewed, but not, you may be doubting. We have a situation like that. Is it normal? Is it skewed? When you have those types, 30 will be enough. But the skewer the distribution, the less normal the population, the larger the sample size you should choose. Okay, so I am mentioning 30 here for our class, but most people use it as their own rule. But it does not work all the time. What is your takeaway from this? You will be given questions like this one. And your question, to solve this problem, you will ask yourself, is the distribution of sample mean normal? If yes, you apply the normal distribution that we have been using. If not, is the sample size large enough? If it is not large enough, you cannot do anything. So naturally, I'm not going to give you a problem that will not work for normal distribution, because that's all what we can do. So essentially what I'm saying is, I will always be giving you problems that you can use the normal distribution, but sometimes I may ask you if you know the reason why you are using that normal distribution. There are two possible reasons. Either the population is normally distributed or the sample size is large enough. Let's look at this example. Suppose a team of biologists has been studying the Pinedale Children's Fishing Pond. Let X represent the length of a single trout taken at random from the pond. This group of biologists has determined that X has a normal distribution with mean 10.2 and standard deviation sigma. Each time you have a question, henceforth, you want to start with what is the mean? What is the standard deviation of the population? So you can see the PowerPoint, can you? You have it on your computer, some of you, because I can't have both at the same time here. And I want to write so that those who are at home can see what we are writing. So can somebody tell us what we need? X is 10.2, 10.2, and sigma is 1.4. So what was the first question? Can somebody help me reading that? I can, anyway, for us, I can read. They are not going to see, but listen. So we can always see. This group of biologists has determined that X has a normal distribution. Will we care about the sample size? When X has a normal distribution, we don't care about the sample size. Do we get that? If X is normally distributed, we might have a sample size which is 5 or 10, and it will work. What is the probability that a single trout taken at random from the pond is between 8 and 12 inches? So the question is, find the probability that X is between 8 and 12. This is a question. Can you find this? If you don't know anything else that they were saying, you have the mean, you have the standard deviation, you know the distribution is normal, you use your calculator. You can use your calculator. If you forget, just ask me. We are in class. If you are at home, go to the PowerPoint of chapter 6. You will see the slide describe how to use calculator. Or you can Google scientific calculator, it will give you one. So you go second function, distribution, normal CDF, lower value 8, upper value 12, mean 10.2, standard deviation 1.4. Somebody having trouble doing that? Can somebody give me the answer? .843. So this is the probability that what? A single trout, this is 1, right? It is 1. So this is for 1. Now, let's look at, this means about 84% of those trout have size between 8 and 12. This is what you were supposed to do if you have to use the table. So for our class, we cannot because we don't have the time. And it's not what you really need to know. That's why I usually skip it. So now, what is the probability that the sample mean length of 5? See why I said saying? I would have said saying, which is French. Sometimes I get confused with that. What did he say? Then it's like that. So that's the language I speak more often. So what is the probability that the mean X bar length of 5 trout taken at random is between 8 and 12 inches? Do you see the difference between these two questions? If you see the difference between these two questions, you have achieved our objective in this section, essentially in this chapter. That is, you can know what it means to take one and what it means to take many. So we are now computing the probability that the sample mean is between. If you take 5 trout What's the probability that the average of those 5 trout is at least 8, at most 12? That is the second question. So to answer that question, we want to know what is the mean of the sample mean. What is mu of x bar? What did we say was the mu of x bar? What is mu of x bar? What is the expectation of the sample mean? 10.2 is the population mean, right? Mu x bar is mu. So it's equals to mu, equals to 10. And sigma x bar is equals to what? Sigma over square root of n. This is what you will forget on your exam and homework. Divided by square root of n. And what is n here? N is 5. Can somebody help us to know what this number is using your calculator? It's always good to do that separate. 1.4 divided by square root of 5. 0.62? Is this 0.626? Okay. We can make it 0.63, but this is called the standard error. If some of you could remember when we were doing summary on Excel, there was one information coming in that I said, forget about it. It was called standard error. So that is what we are actually doing now. But the standard error that we have on Excel was from the sample. So this standard error is from the population. So this number is the standard deviation for the sample mean. So if we have our question now, what is the probability that less than x bar, less than x bar, less than 12? This is our question. We are just doing the same thing using our calculator. The mean is 12.2, but the standard deviation has changed. You have divided it by square root of n. That is the difference. So can you do that using a calculator? We don't want to waste the time with the z distribution. What do you get? 0.998. Do we all have that? Yes. So in chapter 6, we learned about the normal distribution. It is a very good distribution that we will always want distribution to become normal. We are learning that the sampling distribution of sample mean will be normal either because the population was normal or the sample size is large enough. Same thing will apply to proportion. We are not doing proportion. Now we are speaking proportion a little bit, but you can do that. If you are asked a question about the binomial distribution, it requires proportion. But you can use calculator to do binomial distribution directly, even if n equal to 1,000. But we are going to give conditions for a binomial distribution to be normally distributed. But I don't generally give you questions about it because I want you to really know about the mean. Okay. So I want you to feel that difference between when a question will be about an individual or an item, a single selection, and when it is a group for which you will see the word average, mean. It will help us. So let's quickly look at this example. Our first example was with a population. We don't need to do it, but we just want to read and know what we are supposed to do. You already know how to do it. So a certain strain of bacteria occurs in a raw milk. Let X be millimeter of milk. The health department has found that if the milk is not contaminated, then X has a distribution that is more or less mound-shaped and symmetrical. Is it normal? Not sure. But if they don't give us more information, we can assume it is normal because it is mound-shaped and symmetrical. So let the mean of this distribution be 2500 and the standard deviation be 300. In a large commercial dairy, the health inspector takes 42 random samples of the milk produced each day. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain the sample mean bacteria. Assuming the milk is not contaminated, what is the distribution of X bar? The distribution of X bar will be approximately normal for two reasons. Okay, it is mound-shaped and symmetric. I think it's normal. Somebody say, no, how do you know? Okay, I leave that one and say sample size is at least 30. So that's it. Are you getting what I'm saying? Either the population is normal or sometimes you are doubting, but when the sample size is large, that settles. It settles it, and we say that X bar is approximately normal. The mean is the population mean. The standard deviation is the population standard deviation divided by square root of n. This does not have to do with normal or not. That we did that computation without knowing the nature of the distribution. So what is the probability that, assuming the milk is not contaminated, what is the probability that the average bacteria count for one day is between 2,350 and 2,650? So we find the mean and the standard deviation and use calculator. So we are good here. Somebody is coming to class at this time. We are good here with chapter 6. So there is 6.6 that I left out. Is about this population. It is essentially the binomial distribution. When you have a binomial distribution, you can use a normal distribution for it if it satisfies these two conditions. But the main problem about it is the fact that you use the normal distribution, you need to do the correction of continuity, which is sometimes. So if I say n equals to 3,000, p equals to 0.65, find the probability that the number of success is between 7,000 and 10,000. You can use the normal distribution by finding the mean and that distribution for a binomial distribution and apply it. That is what 6.6 is about. If you like it, go and read it. It's optional. Can we have exam on Thursday next week? Let's vote. Because I made it to be Tuesday because I made it to be Tuesday. It's better when we go fast and we have time than when I'm rushing towards the end. Oh no, right? Okay, so we may have to continue with chapter 7. What do you think? Chapter 7 is not going to be on the exam, but we can't stay doing nothing. Do you feel like I'm going too fast? Should we slow down? You are feeling of the understanding and doing the homework, because it seems as if I have made one day extra. I go fast because you are not asking me a lot of questions. If you want me to slow down, ask me questions. Come with homework that you cannot do. Just say, let's do this homework. Then we will go slowly. If we go too slowly, we might not cover everything. Sometimes it's nice when we finish earlier before final exam. We can go to this place and then finish early and continue doing problems. We have all those choices, but I'm advising you, as soon as you feel you are lost, ask questions. Yes, we can go over take-home problem 4 and 5 on Tuesday, go over take-home problem 6 on Thursday. What about that? Yeah, because the reason why I do the take-home problem one day on Tuesday and have exam on Thursday, I am afraid you will forget. That's another side of it. So we will do take-home problem 4 and 5 on Tuesday. We will do take-home problem 6 on Thursday. But Thursday, we may just introduce chapter 7 so that we shouldn't be too much behind. Okay? Yes. Not 2 weeks from now. It's on Tuesday, not Thursday, the 13th. So you see, we are today the 1st. So 2 weeks from now, we will be 15. That will be a Thursday, the 15th. So the Tuesday of that week, so a little bit before. It's not 2 weeks from now. It's 1.5 weeks from maybe. It's more than 1 week. So instead of waiting for the other Tuesday, I was saying, can we do it next Thursday? That's what I was thinking. So we could do the take-home problem. But as we say, we will do it that Tuesday so that we take time to work on chapter 4 and 5. Come with any type of question, homework question, take-home problem. We will do chapter 4 and 5 on Tuesday. And on Thursday, we will do chapter 6. So chapter 6 take-home problem is due on Wednesday because we are going to work on it on Thursday.